Okay, off we go. Hope everybody had a nice weekend. Let's see here. Before we get back into the math, reminder, attendance quiz, attendance code, clock's ticking, you get a minute 45. Okay, let's see here. So, here's where we were last time. We were talking about a particular geometry problem. This is a narrow, particular question. I don't want to oversell it. Right? This is ultimately not what we're going to be interested in the long run. Right? So let me just make that part clear. Nevertheless, let's proceed with this geometry problem. We've got a graph, z equals, right? What am I doing? Oh, I'm in the wrong mode. Sorry about that. Let's see here. I got to get out of that mode. There we go. So yeah, here much better. We're looking at a graph. And we're going to look at the part sitting over a particular rectangle in the XY plane. And the question is to compute what is the volume sitting under that graph over the designated rectangle. All right, so there's the question. We're going to rip off an idea from single variable calculus, which is to kind of take cross-sectional pieces and then argue that on each piece the area times the thickness will give you the volume, and then you add up over the whole to get the entire volume. So ripping that off, we do like so. Now let's see, let me get it to full screen mode. That's better. In fact, let me zoom in a little better. There we go. We can compute that cross-sectional area without that much trouble, really. The point is that if we're going to compute this area, we have to ask first for what value of y do we want the cross-sectional area. And if you think about it, if you designate there's the particular value of y for which I want to compute the corresponding cross-sectional area, what you are doing is you are fixing y. Said differently, you're making y a constant. And now if you look at your formula here for our graph, and if y is now a constant, well, in fact, what we have left is that z is a function of effectively only x. Right? So this is now a single variable function. You may recognize this function. This is exactly the function whose derivative we talked about when we were talking about partial derivatives. And I like the term partial function. It's very convenient and sort of directly to the point. So this function, we've already talked about that its graph is the cross-section of the original graph. So how do we find this area? Well, this is a pretty straightforward question now. How do we find the area under a curve? More to the point, how do we find the area under the graph of a single variable function? Well, integral. Right? This is our old, one of our original interpretations of single variable integrals. Right? Now you got to keep in mind, as we compute this integral, the picture is very helpful here. We're computing this area, and notice for that entire computation of this entire area, y doesn't change. Right? So while we are looking at this integral, don't forget y is a constant. And so this is straight up a single variable integral, x being the only variable. And in particular, you can see x as we proceed across. X is the variable that's changing. So that's an x integral. How are we doing? Is everybody on board? Okay, so we're actually done, believe it or not. We just have to put the pieces together now. And let's see here. Let me clear the board. Let's see here. So our first argument was, I've already forgotten what colors we used, but let me use purple. I like purple. We're going to integrate with respect to y, and integral of area times dy. We're adding up a bunch of little pieces of volume. That was the argument we made here. Right? So for the purple integral, the dy integral, that's what we're doing. Now wait a second, we just computed the integrand. The integrand is this area, and that area we just got through deciding is itself an integral. It's an integral as we go in the x direction to compute that cross-sectional area. And okay, well, the cookie has crumbled such that what we have is kind of weird, but we have an integral of another integral. It's an integral sitting inside of an integral. Weird construction, might be your first time to see such a thing, but that is what does the job. And plug and chug. We're going to do an example in just a second here, but this will compute that volume under the original surface graph. How are we doing? Everybody buying it? Okay. Couple of quick reminders. Don't forget, while you're doing the inside integral, let's see here. Okay, the inside integral, right? X is your variable for the inside integral. The purpose of that inside integral is to compute this area. This area isn't even well defined until you fix y. That is, until you recognize y as being a constant. And so, said differently, the outside variable should be treated as a constant in the inside integral. And that's an easy thing to lose track of, easy thing to forget. This is what I have always found to be the most geometrically satisfying sort of motivation for why would I treat y as a constant? Well, literally it is. Is everybody happy with that? Okay. The other thing before we go on, this is just a kind of a semantical point, but we do have two integrals here, and there is a strong tendency to want to call them the first one and the second one, and I feel like that's pretty ambiguous. For the sake of the argument that we made, we talked about the y integral first, and then having written down the y integral, we said, we're going to need to know my integrand is going to be that cross-sectional area. And then we subsequently decided to compute this as our second integral. So in terms of how we wrote them down, the dy was first. But now let's think about how we would compute such a thing. And again, we're going to do one momentarily. If we're going to start computing, we kind of have to start the computation with the dx integral being computed first, because it's the only one I can, right? I can't immediately start talking, let me do the dy integral. I don't even know what the integrand is yet for the dy integral. That's the dx integral job, is to compute the dy integral's integrand for us. So computationally, the dx integral has to be first. When you're done with that, you know the dy integral's integrand, and then you would compute the dy integral second. So this terminology, first and second, it's really unclear, right? And again, you got to keep in mind, our goal here is to talk about, mathematical reasoning. What you're going to have to do on a test is explain clear mathematical reasoning. And if you say the first integral, it's not clear, I don't know what you're talking about. Right. So, easy solution, and I think there's just nothing to worry about here. Let's just refer to this as the inside integral. Perfectly clear. That's exact. It says exactly what it means. And then likewise, we can refer to the dy integral as the outside integral. So another thing. Yeah? Mm-hmm.
Doesn't matter which way you keep as a constant first.
That's a great question. I am going to come back and talk about that in a minute. For the moment, I want to keep a short answer is, in this case, no. But there is more to say about that, and I'm going to come to that in a few minutes. Yeah. Let's see here. Yeah. Okay. So let's do an example. Here we go. Notice this question is right down the pipe, exactly the scenario that we've already entertained. We don't have to go through a slicing argument again. We've already done it. We already know that if you're looking at a graph and you want to compute the volume wrong color. You want to compute the volume under a particular rectangle, we know that exactly this integral will do it. So we can just start with that. Again, notice that, let's see here, the function whose graph we're looking at is the integrand, right, per this argument here. And let's see here. Now, we do have to be a little careful about the bounds. I am going to have to talk about this notation. This notation right here, you may or may not have seen this notation before. It's very common. It's very convenient. We're going to be using it a lot. This is a notation to describe a rectangle. It looks like a cross product. It's not. There's only so many symbols, right? And sometimes the same symbol gets used for multiple different things. And I'm sorry, it's a little weird looking, but that is a reference to a rectangle. And the idea is that the first interval is the range of values for the first variable, in this case x. And the second indicated interval is the range of values for the second variable, in this case y. So this notation then refers to the rectangle that has those sort of projections, if you will, and so that indicates that orange rectangle. Does that make sense to everybody? Any questions about it? Cool. All right, so if you go back up here to this argument, what you notice pretty quickly is that the bounds for, take your pick, the dx or the dy, the bounds for any one of these integral, it's the corresponding bounds for the rectangle in question, right? X goes from A to B for this rectangle, so the x integral goes from A to B. So that's very convenient, and following that pattern, notice we've got our x bounds from 0 to 1 as indicated. We've got our y bounds, from 1 to 2 as indicated. Everybody all right? Okay, well, so plug and chug. It's a straight up single variable calculus at this point with one little detail that you have to keep track of, but ultimately these are single variable integrals. Very literally, these are single variable integrals. We have not yet defined a multiple integral. This is called an iterated integral, right? But this is not yet a multiple integral. So it's just calculus. Now the asterisk, the one little sort of asterisk you do have to keep in mind for the purposes of this inside integral that we compute first. As I compute that inside integral, don't forget the outside variable is to be treated as a constant. That means that this term right there is to be treated as a constant because for the purposes of that blue integral, it literally is behaving as a constant. So easy to kind of lose track of that, right? It's easy to kind of get into this mindset of, oh yeah, integrals. Oh, that's where you play the game, right? And so, x squared turns into 1/3 x cubed, and it's easy to, I remember those rules, and accidentally, carelessly, sometimes students will write here 1/3 y cubed. And that doesn't make any sense. That's absolutely wrong. It portrays a fundamental misunderstanding of what these things actually mean, right? So it's an easy little whoopsie to make, but it has big consequences. So one of the most important things, your responsibilities as, users of these ideas, is to make sure to remember which variable is playing what role at what stage of the calculation. So this y squared being a constant, the antiderivative of y squared is just x times y squared, because y squared is a constant, and that's how you integrate constants. Happy? Everybody? Any questions? Feel free. Okay. All right. Okay, the other little micro, this is just, you don't have to do this. You'll notice that I did something maybe a little unusual, and that is I wrote x equals 0 and 1 there. I mean, the more common thing to do is just take these bounds and just kind of come over here and write down just the bounds. Right, so why did I write x equals? And the reason is because I lose track of things myself sometimes. We're all humans, we're all fallible, right? And it's just all too easy to take these numbers, let's say the 1 here, and as you're plugging it in, to plug it in for the wrong variable. Right, it's real easy to do that. This 1 is specifically representing values of x. This 1 should be plugged in only for x. Y is not going from 0 to 1. Y is a constant, right? So we don't plug in for it. So this writing down x equals here is my little sort of reminder to myself, hey, don't plug this in for the wrong thing. I find it helpful to me. I hope you might find it useful, helpful to you. Again, it's just a personal method. It's not anything that's important. Notice that what we're left with after we finish computing the inside integral, right? You compute the inside integral, and now we have a perfectly satisfactory integrand for the dy integral. It's a function of y. Y is now playing the role of a variable. Y is now ranging from 1 to 2 now that I've done the inside integral. So y being a variable, we treat it as a variable, and now the integral of this y squared is 1/3 y cubed. Is that cool? Is everybody on board? Everybody with me? Okay. All right. And then details in arithmetic, blah, blah, blah. Okay. All right. Somebody asked earlier, can you do this in the other order? Absolutely. This is a fabulous little exercise. Now, what I just got through arguing was that volume can be computed as an iterated integral where you do your slicing in this particular order. If you want to take the I've forgotten the colors I used. Anyway, it doesn't matter. If you want to take the outside integral and make it the inside, and the inside integral and make that the outside, right? Just slice sort of in the other order. You can go all the way back to here, draw the corresponding pictures. This is a fabulous exercise. And by the way, feel free to use this as kind of your guide, right? And just realize everything's going to be kind of turned the other way, right? But you can use this as a template, reason by analogy, draw the corresponding pictures. The area is going to go the other way, the integral, blah, blah, blah. And what you will find is you get exactly what you would expect and hope. So you can do it dx dy, or you can do it dy dx. And what's nice is you will have the same integrand in both cases. And you'll also, and I'm going to be really careful how I say this, you'll have the same bounds in the sense that y will be going from c to d in both cases, right? And x will be going from a to b in both cases, but they've switched places, right? So a to b was on the inside, now it's on the outside. And the point there is, of course, that it stays with the variable that it represents values of. So if you switcheroo the variables, the differentials, well then of course you have to switcheroo the differentials, the bounds as well. Does that make sense? Everybody buying it? Okay. Does that answer your question? Yeah. Okay. All right. The asterisk on this is arguably a premature point, but this only works when the domain is a rectangle. It's very important. Only when you're dealing with rectangles. Now, to be fair, so far we have only asked about rectangular domains, right? So, okay, fine. But very soon, possibly today, we're going to start talking about non-rectangular domains. And in those cases, you absolutely cannot do this. The switcheroo, no, the bounds are going to be totally different. And it's complicated, and we'll get to that when we get to it. Okay. All right. Now, there is a subtlety here. Oh, yeah. Oh, I'm sorry. Sometimes it really depends on the situation. So if you look at the integrand, right? So the integrand is a function of both x and y. There are cases where when you do the dx integral, that can make the dy integral easier. Well, if you had done the dy integral first, it would have been a problem. All right, so stuff like that can happen, right? So I don't want to say it. I absolutely cannot say that one is better than the other. But in any given situation, who knows? So it's a good thing to always kind of keep your eye on and kind of be on the lookout for, wait a second, which way would be the easier way?
But typically you do DX then?
Nope. There is no typically. It really doesn't make any difference. So I don't want people saying I'm a DX DY kind of person, because there's always better considerations, and generically there is no rule for one being better than the other. Does that make sense? Yeah. Okay. So here's a subtle problem. Y'all remember in single variable calculus, once we wrote down this idea of an integral, oh my gosh, the integral you could compute all sorts of stuff with it. And for example, the mass of a one-dimensional rod, where you're given the density. And the integral that we used to compute the mass of a rod was exactly the same construction that we used to compute the area under a graph. It's the exact same construction. You just put the delta where the f had been, right? Same thing. All right. Well, that was really nice. I wonder if that pattern continues. What if we have a two-dimensional rectangular sheet? It's kind of a two-dimensional analog of a rod of non-constant density. It would be a sheet of non-constant density. And golly, in single variable, how much area under the graph and what's the mass of a rod, they use the exact same construction. So maybe in this two-dimensional case, maybe the mass of a rectangular sheet, maybe we can compute that with the exactly analogous construction. I'm going to put a question mark here because this is just a hope. Right? I mean, it seems like it ought to work. I mean, this computed the volume under a graph. That we know. By analogy with what happened in single variable, can't we just do this? And, yeah, you would think so. But, no. Very important point. I know I say this a lot. I say it a lot because it's important. This is a class about reasoning, not answers, right? As an answer, this will compute the right answer. That doesn't make the reasoning acceptable, right? And I claim that if you just right off the bat say, oh, you want to compute the mass of a rod? Oh, okay, well that mass is this iterated integral because, of course, I have questions. I don't think that's clear at all. And the easiest way to see this, as I like to understand this, is, if you look at the very first thing, the core sort of deepest inside the expression, what's going on here, the argument we made in the single variable, in the geometric case, in the volume case, was that that was a height, and the dx was what I'm going to call a length. And then from that, we argued that, height times length is area. Area is a thing. It's a known thing. I have pre-existing intuition for it. I can make a case for how area behaves. And by the way, among other things, I know that area has this feature called accumulation. I like to call it accumulation, which just means the whole is the sum of the parts. So let me come back to this picture up here where we argued that, again, we're going to compute the area as that integral. I think it's very intuitively clear, very intuitively satisfying that if I chop this area up into little pieces, the whole is literally the sum of the parts. That's how area works. Perfectly clear. Right? Okay. Well, oh my gosh, can I do something analogous here? And the problem is I can't, because this density came to us as mass per unit area. So mass per unit area, if I multiply that times length, what does this give me? And I don't really know. Mass per unit area is a thing that you're supposed to multiply by area. If you ask me, hey, what do I get when I multiply mass per unit area times area? I'm going to say mass. Right, that's mass per unit area's job, is to be the thing you multiply by area to get mass. When you say mass per unit area times length, I don't know what that is. You could make a case for maybe it would be mass per unit width, maybe, right? Okay, but what is that? Mass is not distributed across width. So what is this mass per unit width? By the way, how does this new construction, this mass per unit width, how does that behave? Is that an accumulating quantity? This is not clear. I don't know what that is. Does everybody see what I'm talking about here? That's a problem. And you might even be able to, make a compelling case and argue all the little details of that, and persuade a reasonable listener that you have a coherent argument. But the problem is, mass is not the only question that we're going to have to make these kinds of arguments with. So every single time you want to compute something that isn't volume, we don't want to have to go through and check a bunch of details and take a non-pre-existing concept and try to argue that we should have a good intuition for it. This is not a good plan, right? So I'm going to call this a fail. This is, at best, a very inefficient way to approach generalizing the volume argument. Everybody see my gripe on that? Yeah.
I just don't really understand what's wrong with mass per unit width.
So tell me what that is. I mean, what's the mass per unit width of this desk, and how should I think about that?
I mean, you could kind of calculate it, but the width would be the change in y, right? So then,
I don't know what you're talking about. No, what's change in y? We're just talking about this right here. And by the way, we're going to add up a bunch of these before we then subsequently start talking about multiplying by dy. Right, so if you're going to make a mathematical argument, then you're going to be doing stuff with stuff you've defined. You have to understand the stuff before you do stuff with it, and you can't then say, "Oh, it's going to make sense later."
Okay.
You see the problem? Now, again, I'm not saying it can't be done. Right? I probably could. I'm sure we could all probably sit down and write some definitions and do some examples and, persuade a reasonable listener that here's how it's going to work. But the problem is we don't want to have to do that. It's definitely not obvious, right? Whereas if I say height times length is area, yeah, sure, of course it is. This is a pre-existing concept. So really it's the comparison between how natural and clear and seamless this is versus, roadblocks and problems and inefficiency here. Is that satisfying?
Yeah.
Okay. Yeah. Yes?
What is dy? If dx is length, then dy is width.
Well, I guess you say it's width. I mean, it's whatever you feel like calling it. And, you look at this picture here, but it represents, when I say integral area times dy, it's differential in the y direction when you take your original volume. Actually, I guess I should go up to, when you take your original volume and you slice it up into slices, dy you can think of as representing that. I guess we'd call it width. Yeah. Right. Good news. There's a way around this, right? So this problem that I've identified, the point to this is let's find a better way to deal with this. And there is one, and it's ultimately pretty natural. Okay, so, by the way, we're done with section 5.1 now. So let's talk about section 5.2. I hope you all remember the definition of an integral. Riemann sums. By the way, there's lots of different definitions of integrals in different situations, but depending on the assumptions that you make about the function. And by the way, when f is not continuous, does this make sense anymore? Problems come up, as it turns out. And there are ways of fixing that. And then there are other ways that we might want to relax the question and then ask, well, how do we fix those problems? And there are strategically different constructions. There's a whole field out there called measure theory, right? It's sort of a subset of real analysis. And it's very sophisticated, very classical, beautiful mathematics. But thankfully, we don't have to worry about any of that. So in this class, we are going to define integrals for continuous functions. Anything I say about continuous, by the way, also works for piecewise continuous, which in the real world, that's all we're going to have to worry about. And for those functions, this is just as good as any other definition that anyone could ever come up with for an integral, and it's the easiest one to write down. It's the one that's most broadly useful and applicable. So this is the definition that we're going to work with. Okay. Does that look familiar to everybody? Yeah.
Wait, sorry, this is kind of like a small thing, but should the sum start at I equals 0 so that x sub I equals a, like as the first?
I hear you. It is, let me come down to here. So for any given subinterval,
yeah.
Right? So if I look at this subinterval right here, I'm going to call that the first subinterval, right? And arbitrarily, I'm going to use x sub 1.
Oh, okay.
Right, at that point. But so for every subinterval, I need 1 point. And I could have chosen the left endpoint, in which case I would have started with x of 0, but then I would end at n minus 1.
Yeah.
And so, all else being equal, I think it lays on the page a little bit more conveniently if you do it like this. Yeah, totally. Okay. Very important definition. It's important for mathematical reasons and, rigor and purity and blah, blah, blah. And I know that's not what the great majority of y'all are mostly here for. So let me try to make this compelling case. I think this is very compelling, even if you don't care about, math, rigor, and stuff like that. Perhaps you might want to be able to use integrals to solve real-world problems. I bet you most of you do. Well, it turns out this is a really great way to get your hands on real-world problems. And in particular, whatever your application might be, and there's a bazillion applications. I mean, I just wrote down a handful here, right? But there's bazillions of applications of integrals. Let's talk about mass. We've talked about that one before, mass of a rod. You can take a one-dimensional rod, right? You can chop it into little pieces. Each little piece, you can say, well, the density is approximately constant. On each one of those little pieces, you can write down the mass of that little piece, approximately, close enough, as density times length, because in that one-dimensional case, density means mass per unit length. And then you can add them up, and you are, in fact, literally writing down a Riemann sum. Right, so when you use an integral to compute a real world problem, it is the Riemann sum construction that allows you to make that connection, right? And that's why, very importantly, I think, integrals are defined as Riemann sums, because that's what connects to real world scenarios. Like I want to compute mass, or I want to compute population, or whatever. Right? So here's what you can't do. And again, if you just want to make a coherent mathematical argument, you can't say, want to compute mass? Okay, well, mass, of course, is equal to area. What? Why? Where did that come from? No, it isn't. They don't even have the same units. It's totally different stuff. Right? So this is, you can't do that. Now, the closest thing to it, you can take the mass that you want to compute and kind of as much as, but maybe just don't quite come out and say that you're doing a Riemann sum, but effectively make basically a Riemann sum-like argument and then connect it to area. And then, subsequently, I suppose, if you really want to, you could say, and by the way, I can compute that area with an integral, but I feel like this was a completely unnecessary little detour, right? You don't need area to make the argument. Area contributes nothing to the argument, right? Once you've made the connection that mass is a Riemann sum, cool. Fundamental theorem. Answer. victory. Area's got nothing to do with it. All right. So, no, don't get me wrong. I mean, when I taught single variable calculus long ago, sure, I drew lots of area pictures, right? Because it's a picture and it's something you can see, and it is a nice metaphor for integrals. It's a nice visualization tool for integrals. But don't overinterpret, please. From that, area just is not what an integral is. And it's important. Computationally, forget about, mathematician, rigor, fussiness. That's not the point. From a computational standpoint, this doesn't make any sense as an argument, but this, I wanted that to be in green. This is fine and dandy. So that's why you should care about Riemann sums, if I may. I mean, that's just an opinion. Okay. So, the reason I make a big deal out of this, I mean, part of it is, y'all are coming from single variable calculus classes as your last calculus classes. I think there's a lot of students out there. By the way, I was one of you, right? When I got out of single variable calculus, I was under the mistaken impression that Riemann sums were an outdated, obviated by the fundamental theorem of calculus, now useless method. This is absolutely wrong, and by the way, also historically inaccurate. This didn't come about until the 1800s. Newton came up with the fundamental theorem of calculus in the 1600s. So there's that little point for your consideration. So, okay, I hope that cleans up maybe some misunderstandings about single variable, but my immediate motivation here is that when we're going to write down a double integral, I'm going to try to make a new concept, we're going to define a new kind of an integral, we have to know what we're generalizing. And the question is not, how can I generalize the idea of area under a curve? The computation we already did, volume under a graph, it's not the point. The point is, I want to be able to generalize the idea of a Riemann sum. This is the thing that's going to connect to applications. If you want to get stuff done, which I imagine y'all probably do, Riemann sums are what's going to do it. And then, by the way, we're not going to write them down as Riemann sums. We're going to write them down as integrals, and then we're going to compute integrals with nice, powerful integration techniques. Yeah, for sure. Right? But making that immediate connection and being able to relate a real-world problem to a math problem, Riemann sums. Okay, enough of that stump speech. Here's the way to think about it. We've talked about single variable Riemann sums. Again, this is a Riemann sum representing a summation over an interval. And let's see here. Let me just do a little highlighting. For each little piece of the interval, whatever the application might be, we're going to be multiplying something times the size of that interval. And let's just think through a couple of examples. Where have we taken a function and multiplied it by the size of that interval? Well, if you're computing area under a graph, then it's height times the size of the interval. If you're computing the amount of mass, total mass, starting off with what's the mass inside of this little subinterval? Well, I'm going to multiply mass per unit length times the size of the interval. Pick any application you've ever done with a single variable integral. The integrand is the thing you multiply by size to get stuff, whatever the stuff is that you're actually adding up. Every single application of single variable integrals. All right, so we're just going to kind of do the same thing over here. We're instead of taking up an interval and chopping that into pieces, we're going to take now a rectangle and we're going to chop it up into little pieces. Now, when you chop into little pieces, you slice both ways, like so. And again, we're going to make the same kind of argument that we did previously. in the single variable case, how do I compute the total mass? Well, I compute the mass in each little piece and I add them up. And then likewise over here, it's going to be the exact same thing. One at a time, I'm going to write down how much of whatever the stuff is maybe I'm computing mass, maybe I'm computing the population of Colorado. I don't know, whatever, right? I'm going to figure out how to do that on each little piece, and then I'm going to add up over all of the pieces. Fundamentally, that's what a Riemann sum is. So let's see here. So on each little piece, right, there's a little piece. Whatever it is I want to compute, I like the mass metaphor because it's viscerally kind of relatable. I want to compute the amount of mass in that piece of area. Well, I'm going to compute that as mass per unit area times area. The area is the width times the height. The width is just delta x. The height, length, whatever you want to call it, is going to be an analogous thing in terms of y, delta y. Yeah, there's a bunch of little formulas you got to write down. I mean, the act of chopping up the interval from a to b gives you various formulas about delta x and x sub I, blah, blah, blah. Y'all have seen that before. Analogously, slicing this way chops up the integral from c to d. And again, there's a bunch of little details. What is delta y? What is y sub j? Blah, that's just details. But once you've got all those details written down, it's just stuff per unit area times area that gives you stuff. And then that, once you know how much stuff there is in each piece, you add up over all the pieces. Strategically, same basic idea. What do you think? Everybody see how it's the same basic idea? Yes?
Just a little confused by the addition of like ij equals 1, but then above it's just n.
Yes, that's notationally, I guess, could leave a little something to be desired. So I need I to go from 1 to n. And what that looks like over here is I need to go all the way across, right? But I need to do that not just for one particular value of j, right? I need to do that for all possible values of j, as j also goes from 1 to n. Does that make sense? Yeah. And because, I mean, there's no getting around the fact that while there was only n pieces over here, there's actually n squared different pieces here. Or you might say there's n pieces on each of n rows. And so there's n squared. So that's why the 2. Does that make sense?
Yeah, so think of it like row by row.
Yep, totally. And there, the order that you added up doesn't matter. Okay, so this construction right here, now I know we haven't done any examples yet. We'll do an example in just a second here. But this construction right here, I hope you're at least optimistic, because this is a kind of a natural extension of this idea. This idea proved itself useful, mega useful, right? This is a pretty natural generalization. We should be optimistic that this will be super useful as well, and it will be. Okay, so we're gonna, with that in mind, with that optimism, we're gonna take this. We're gonna call that the definition of this new thing called a double integral. This is not what we just wrote down a few minutes ago. That's not an iterated integral. This is not a single variable integral of a single variable integral. This is a new critter where we don't chop up intervals into subintervals. We chop up areas into sub-rectangles. And then we multiply stuff per unit area times area. Okay. I think the notation's pretty natural, right? That's what the delta x, delta y was. It's representing little, pieces of area that eventually we're taking limits of, and we're adding up in 2 different directions, right? So thus, I'm going to use 2 integral symbols. That's just notation. By the way, at sufficiently high level math classes, they won't even use two symbols. They'll just write a single integral symbol, and it's understood that, well, of course it's a 2 index. The domain's 2-dimensional, and they just don't even bother writing that. But our textbook, and I think most multivariable textbooks, and I think this is a good idea, write 2 integral symbols as kind of a visual reminder. Okay, yeah.
What's the R?
That's the domain. So whatever the rectangle is over which you're doing your summation. Yeah.
So you're just writing R instead of like A, B, C, D.
Yep. It's just, it's convenient. Yeah. Okay, side note, you don't need to worry about the book. In several places, the book gets a little bit more abstract and mathy than is our focus. So the book takes a few steps in the direction of doing some cool real analysis, Math 431, Math 531 kind of stuff, and talks about irregular partitions and test points. We're not going to do anything with that. We have no need for that. It's not going to matter to us. So you can ignore all of that. Here's our first example. Some people would call this a silly first example because we already know the answer to this question, but how do you find the volume under a graph sitting over a rectangle? We already did it, right? We did it with iterated integrals. But let's show that double integrals can do it too. And in particular, I'm going to take this rectangular domain, I'm going to chop it up into little pieces, and on each little piece, I'm going to argue that the volume in that piece, this little piece of volume, right, that French fry right there, the volume is height times the area of the base. A little geometry argument. Familiar geometric concept, right? Volume. Oh, no volume. Nothing creepy about volume. I claim volume is area times height. Yeah, sure, of course it is. Old news. Right? And then you notice, oh my gosh, look at that. That's exactly this construction we wrote down over here. And so I can rewrite that as a double integral. Is that cool? All right. So why does this matter? Here's why it matters. There's a lot of ideas going on at the same time here. I like this diagram because it kind of keeps track of what's connected to where and when. What we've argued with double integrals is that for many cases, we anticipate anyway that we're going to be able to rewrite applications as double integrals. Now, long ago, as in earlier today, right, we computed volume as an iterated integral, which of course we can compute. But just now, I argued, seemingly pointlessly, that volume could also be computed with a double integral. And now check it out. I've taken a question. I've come up with 2 different solutions to the same question. The question only has one answer, right? So whichever way you compute, these have to give the same answers. Said differently, double integrals can be computed with iterated integrals. That was the purpose. That's the role that the volume question served. It allowed us to make this connection, which otherwise is formalities, and you have to worry about limits and moving things in and out of limits, and it gets a little hairy and technical. And frankly, it's pretty opaque. It's just a bunch of algebra. But I think this is very satisfying. So now that that's done, look, this is what we really care about. Right? This is how we're going to actually make arguments. Whatever your application is, write it as a double integral. Note that double integrals can be computed with iterated integrals, and then we plug and chug just like we did at the start of class. Is that cool? And just a quick reminder, you absolutely cannot say, I'm going to compute mass as volume. That doesn't hold any water. That's there's no argument there. That's a baseless assertion, which happens to be true, but it's still a baseless assertion. And you also can't just immediately write down, mass is an iterated integral. Now, again, it doesn't hold water. That argument doesn't make any sense. Okay, so now, this being a course in multivariable calculus, y'all are doing multi for the first time. There is no presumption in a multi-class that you, of course, understand multi, right? That's not how a test should work, right? Now, there is a presumption that you know algebra. Of course, yeah. You don't, fine. You can do your algebra as fast as you want to do it, whatever. But you do have to make, as far as significant, meaningful multivariable calculus arguments go, you do have to give me the whole thing. So, very importantly, when we start doing questions, which we'll, I guess, do next time, I need to see all three of the steps for the argument to be complete. I'm going to need to see you rewrite the question as a double integral, then rewrite a double integral as an iterated integral, and then rewrite an iterated integral as punch it up, compute the answer. Okay, we'll draw the line right here. Pick up here on Wednesday. Y'all have a good rest of your day. See ya.